Dear all, this is the first tutorial from the series of tutorials which will follow. This series is about the numerical modeling of fracture using Abaqus. We will start with the very basic modeling of geometries using Abaqus CAE. In the coming tutorials, we will perform analysis of the static crack and crack growth. We will also perform post-processing in different tutorials to explore the possibilities of better presentation of results. This will include the generation of graphics, setting and changing fonts and formats of graphs, and if necessary, using the macros to perform the post-processing. So let's get started with the first tutorial. This tutorial is about getting familiar with the simple modeling options available in Abaqus. The schematic of the geometry of the model can be viewed on the screen now. We will apply the uniaxial loading on the top surface and hold it fixed from the bottom. In this case, when all the areas of the model have homogeneous properties, we will not observe any inhomogeneity in the stress distribution. And then we will try to generate inhomogeneous behavior by changing the assigned Young's modulus in different locations of the part. So the main aim is to show you different options for geometry modeling and the sequence of FEM simulation in Abaqus. This will be especially helpful when we will perform simulations in the upcoming tutorials. In the upcoming tutorials, we will also follow the same sequence of actions. First of all, double-click on the parts and select 2D planar option from modeling space. The type is deformable and base feature remains as shell. Depending upon the analysis, 3D or axis symmetric options could also be used. We would like to perform the deformation of our model, so this will be modeled as type deformable. In case of applications like contact problems, for example indentation modeling, deep drawing, etc., the tools are sometimes modeled as analytical rigid. So from the base feature, we select shell. If we perform 3D solution, we will have the option of solid as shape, which can be generated by for example by extrusion of 2D geometries. The approximate size can be 10 in this case. This has nothing to do with the analysis, and this is just the size of the drawing window. From the available geometry creation options on the right, select rectangle using the 4 lines options and draw it in the sketcher. If you hover or bring your mouse cursor over any option, you can read its name. So we use this create lines and rectangles, and we make a rectangle. Since we have the geometry with the dimensions of 1 cross 1, we can click on Add Dimensions tab and give dimensions of 1 both to the horizontal and vertical directions. Clicking the middle mouse button will set it fixed. So now we have our geometry. In the next step, we would need to perform the partition of the face to get the required geometry. So in that case, we go to this partition face menu, and this brings us back to the sketcher again. Now whatever we want to draw, this will be translated as a partition. So we draw a vertical line according to our geometry. And some horizontal lines. These will give us the point of intersection. To find the intersection point for creation of geometry, generate some more lines in the horizontal and vertical directions as shown. Now again, select the Add Dimensions tab and give dimensions of 0.25 to the lines from the top, bottom, left and right to the newly generated lines. And now we can find the intersection points to make the geometry as given in the task. Furthermore, now we would also need to delete some of the lines which are extra, otherwise there will be too many lines in the geometry which we do not want. The lines can be deleted by using the option of auto trim like this. However, if you trim a wrong line which was required for you, then you can use Ctrl Z option and undelete it. This Ctrl Z option works for this case. Now we will delete all the unnecessary lines so that we get the same geometry as required in the task. Now you can see there are 5 different areas inside a single part, and that completes the geometric description of the part. Next step is the creation of materials. We will create 2 different elastic materials having same Poisson's ratio but different Young's modulus. Double click on materials and under materials behavior select mechanical, elasticity and elastic. We give the first material the name of inclusion, the Young's modulus of 210 gigapascals and the Poisson's ratio of 0.3. In the same manner, we create another material, we name it as bulk and give it a Young's modulus of 240 gigapascals and the Poisson's ratio of 0.3. This completes the material description of the part. The next important step is the definition of sections. From the category, select solid. Under type, it remains homogeneous. This selection depends on the type of analysis you are performing. You can name the section as inclusion and then define the material for that also to be inclusion. Similarly, we create the section for bulk and assign the material bulk to this section. Now we have defined the sections, but we did not connect our parts with the sections. We can do is by going to the parts, part 1, and then to the section assignments. And it asks us to select the region to assign a section. We select the middle region and assign it the section of inclusion. And then we select the surrounding regions with the shift key and then assign the bulk section. And we see that as soon as all the regions have their section, the color turns to green. This completes the assignment of sections. The next step is the definition of assembly. Click on Instances and select Dependent Mesh on Part option. In one of the next tutorials, I will explain the option of Independent Mesh on Instance. Now we define the steps, which means the type of the analysis and if it is a single step or multi-step analysis. We can give the name of the step as monotonic loading. It will be inserted as a new step after initial, and the procedure type under general is static and general. The total time period of the simulation is 1, and under incrementation we can increase the maximum number of incrementations arbitrarily high with the initial increment size of 0.001, the minimum time step to be 1e minus 8 and maximum to be 0.01. It means now that if our total simulation time is 1 second, with the maximum time step of 0.01, we can have 100 steps which will be required to converge the simulation to reach the maximum time step if everything is fine. However, if the simulation experiences any nonlinearity and it starts to reduce, the minimum time which we allow it to have is 1e minus 8. That completes the definition of steps. Depending upon the type of the analysis, we will require different types of outputs like stresses, strains, forces, or displacements. This can be set under field output request. Here we select which output we want and even how frequently we would like to output a specific quantity. We can select the step for which you want to have an output, and we land to the Edit Field Output Request tab. Here we can select, for example, the stresses that we need, the strains that we want, the displacements, forces, among others. And we can output the frequency after every increment, or after a specific number of increments, or evenly spaced time intervals. That completes the field output request section. Come to the point of application of the boundary conditions and loads. As shown in the sketch, we will constrain the bottom surface fixed from moving along y or 2 direction. So by clicking the BCs, we can create the boundary condition. The name of the first condition is y constraint, and we apply it in the initial step as displacement. We click on the continue. We select the 2 surfaces at the bottom and apply to U2. So we see that the bottom surface is constrained. Similarly, we apply in the step initial the second boundary condition, which is X constraint, and we apply it to the surface on the left, in this case U1. And finally, we apply the boundary conditions in the step of loading. This will be loading. We apply displacement, and we apply at the top surface along the direction 2 a displacement of 0.1, which means displacement of approximately 10% because the total height is 1, so it will give us the strain of 10%. That completes the application of the boundary conditions. So now we mesh our geometry, which is a very important step. So you open parts, and here part 1, and at the very last you see this mesh, which is empty. So we double click this and this window opens. So since we selected mesh on part, we need to select part here, and then it turns red. By selecting seed part, it is possible to give an approximate global size of the elements. If we click on apply, we see that the size of elements is a little big. So we can change this to 0.01, apply, and this gives a relatively smaller element size now. We click on OK. And from here, mesh part, it asks if it is okay to mesh the part. We click on yes, and it meshes the part for us. And that completes the meshing of our part. Go to the bottom of the model window and click on analysis. Double click on jobs. At the create job, you can give the name as inclusion bulb. Click on continue and OK. Now the job is created. We can right click it and submit it. It shows here that the job is submitted and now it's running. We can monitor the progress of the job. In the first place, the Abaqus tries and checks if all the boundary conditions and required steps are carried out. After that, it starts the calculation of the job, and we can see that the increments are increasing, and here is the time increment that Abaqus is currently using, and here is the step time. So the total time that we have given is 1 unit, and until now it is 0.26, and when this reaches to 1, then the job will complete. So now if you need some graphics for the report, you can go to File, Print, and under Settings, select the file as destination instead of printer, and then you can give here the name and give the format which you want to have. There are a number of formats, which is scalar vector graphics or EPS high definition or PostScript and TIFF, whichever works for your report or your format. That's possible. Now if you want to change the number of division in your contour plots, you can go to options in the menu and click on the contours, and then under basic you can change the number of the contour intervals that are required to get a more fine or a more rough kind of distribution. So you see that the number of fringes have increased. Furthermore, you can also change the limits of the contours. So instead of being automatically calculated, you can fix it to a maximum and a minimum value if you want, and then the contours might change accordingly. Now if you would like to switch off the meshing and would like to have a look on the contour plots without overlaid by the mesh, you can go to the options, go to common, and then from render style you can switch to filled, and then under visible edges to no edges. And now when you apply, you can see that the mesh has been removed. Okay, now if you would like to plot the global stress strain curve, you need to extract some results from the ODB files. So what we will do is we will extract the forces and the displacement and then convert those forces to stresses and then displacements to strains. So for that you would need to go to Tools, XY Data, Create, and then it should be the ODB field output. Click on Continue. From here you can select from the position, you can select the unique nodal, you select the displacement U2, edit selection. So you need to select the nodes for which you want to calculate the displacement. Since it's displacement and it would be same for all of these nodes, so just selecting one node is enough. Now if you click Save, that displacement is saved. Similarly, we would need to write some of the reaction forces. So we select RF2, we uncheck the displacement, and then we again go to the node selection, we remove the old selection, we add the new selection, and it asks us to select the nodes in the viewport, and we need to select all the nodes at the bottom because we are going to average the force, and then based on that force we will calculate the average stress in the vertical direction. And we also click here Save, and that is saved in the database. So how can we access it? So for that, we go to options, we again go to XY data, we go to create, and instead of now generating a new data, we click on operate on XY data. And here we have all the data that we just extracted. So we can see a lot of entries for the RF2. So what we do is we select from the right side, we select average, and then we select all of these forces through the shift key. We click here, add to expression, we save it as force. And if we divide this force by 1, which is the cross-sectional area, that would be stress. So actually, this would not only be force, but this will become our stress in the second direction. And we already have our displacement in the vertical direction. And if we divide this displacement by 1, which is our initial length, this will become the strain. So this is already our strain in this case. Now we have stress and strain, and we need to plot it. But we have stress versus time, and we have strain versus time. So if we click here and plot it, it does not plot here. Okay. So we say that we combine, and we on the x-axis we have strain, we double click this, comma, and we double click on stress, so we have stress versus strain, and we plot the expression. This is how our stress strain plot looks like. Since it was a linear elastic case, so we expect also to get a linear elastic curve. And here we can double click this and go to title. Instead of force, we can have stress S22. And here, instead of force, we will have the strain. In this way, we can get the stress versus strain diagram. And that ends the post-processing, which is a relatively simpler post-processing scheme, but I could show you how you can explain or export the different contour plots, how you can export to a specific file, and how you can extract the data from the database file and do some simple arithmetics like averaging of forces and then cross-plot the stresses and the strains.